Good afternoon, I am Mr. Ish. Thank you for watching this video. In this video, I want to provide you with a useful conversion perspective, that conversion which involves exponential functions. As you go through this video, you'll see some of the benefits of this conversion. We're dealing with conversions between exponential functions and power functions, primarily power functions towards the direction of exponential functions. Exponential functions have the form of such as you're seeing. Power functions have this type of form, as you can see right over here, power functions. Power functions are technically exponential functions, but you can differentiate them in terms of what serves as a base. Here you have a base e, here you have a base which can be a numerical item. Power function, exponential function, there's a good conversion which can arise such that you can view all of these type of power functions as being exponential functions. Let's talk about that in this video and some of the benefits that you can derive from this conversion. Very quickly, 0, 1, a good y-intercept. If you were to graph exponential function, it would look very well like that. We don't have to be very accurate here with regards to the rate of change that's shown. Now, if you were to graph, let's say 2 to the x and 3 to the x, these are power functions. A to the x or b to the x, they're all power functions, but they're all in a way exponential functions. 2 to the x, let's actually add into this mix 1 to the power of x. To the power of x is always 1. Therefore, this very well boils down into y equals 1. Again, all of these will go through 0, 1. Y equals 1, which is the same thing as this. 1 to the power of x is shown here in this dotted line. Let that be the standard from which everything else will arise. 2 to the power of x. Again, we're not being 100% accurate, but I'll try to be. 2 to the power of x will look something like this. Right here, 2 to the power of x. 3 to the power of x would look something which will come right over here, and then it will shoot up in this direction, 3 to the power of x. E to the power of x will fall right between 2 to the power of x and 3 to the power of x. And why would that be the case? The case would be such that if you were to think of e as a numerical number having the quantity 2.71828, I believe that's a number, it's more closer to 3 than it is 2. So you're really looking at something which is 2.71828 to the power of x, which basically, you know, is a power function. That's why the curve of e to the x is closer to 3 to the x. But you can see this right here is 1 to the x. As you increase the base, the magnitude of this base in terms of its numerical quantity, you see 1 to 2, e, and then 3. As you increase this, your curve will become more and more steep. We have all of these power functions in a way they are similar to, or they can be converted into this, and that's what we're looking at over here. This graphic perspective here is just to show you how each of these forms, which are relatively just same as this, 1 to the x, 2 to the x, 3 to the x, these are all in the same form as that, except here using a variable to denote a number which would have ideally existed as your base. But all of these are technically this. We just have to see how that conversion can take place. Let y equal, and I like this form right over here. Books usually go a to the x or b to the x. I technically prefer to use this. Anyhow, let y equal b to the x. Ln y equals x ln b. Solve for this y. You take the natural log on the other side. You have e to the power of x ln b. And this right here, this expression shows you very well the conversion between a power function and an exponential function. Therefore, y equals b to the x is same as or equal to e to the x ln b. That's exactly the conversion you want to keep in mind. If you have b to the x and you have e to the x shown to you to be equal, which they are, bring them over here and bring in the natural log. X ln b is equal to x ln b, this entire exponent coming down as a coefficient ln e. Ln e is a 1. X ln b equals x ln b. So we know that this conversion perspective is indeed true because we have verified it. Let's come back to this conversion that I've shown you, and now let's put in some numbers. Again, this is a very useful conversion to know because it can have a variety of intangible benefits as you do your calculus or your pre-calculus math. What are we seeing over here in terms of what comes out? This becomes that. The base over here gets replaced by an e, and this base over here ends up as a numerical quantity after your natural log. Therefore, if you had something which looked like this in terms of exponential e base, this would become e, and it would become x ln 2. If you had 3 to the power of x, it would become e to the x ln 3. This base becomes a numerical quantity after your natural log. X just has its position retained and the natural log 3 comes in it. So if you have something which looks like 14 to the power of x, you know that in terms of base e, it would be e x, l, and 14. If this little conversion process confuses you, always think of it in this way. You do this and you bring the natural logs l and y is equal to x, l, and 14, and then you solve for that y. All of this becomes an exponent with the base e to it, x, l, and 14, and you can see the conversion process is not difficult. You by no means have to memorize this conversion process, like what happens, what exactly happens, because you can easily derive it by solving for y in terms of the natural log going on the other side as an exponential base e. Okay, now that we've established that this conversion process is good, we have to show you how it can be utilized. Consider this case right here, 2 to the power of x times 2 to the power of x. You can't do much with this mathematically because the bases are different, right? If supposedly you're looking at 2 to the x times 2 to the x, you can do something. You're looking at 2 to the power of 2x because the bases are the same, the exponents add. We know that from the laws of exponent. But when we're looking here at this question over here, you can't do much or different, but if you were to convert them into expressions having the same base, then you can do something. 2 to the x will become e to the x, l, and 2 times 3 to the x will become e to the x, l, and 3. Now you have similar bases coming into play. You can do e and you can add the bases x, l, and 2 plus x, l, and 3. You can even simplify it by isolating an x, e, exponent x, l, and 2 plus l, and 3. See, now you had something which had different bases. You couldn't do much, but after utilizing this useful conversion perspective, you can do something with it, and now you've actually brought an expression that has been simplified with regards to this. Okay, so that's one thing we've seen. Let's look at something else. How about this? 2 to the power of x divided by 3 to the power of x. Again, you can't do anything here because the bases are different. Anyhow, convert them into their exponential forms. We'll convert these power functions into their exponential forms. You'll have e to the x, l, and 2 divided by e to the x, l, and 3. Remember, in this video, I'm showing you this useful conversion perspective. Then I'm showing you what can be done. And of course, I'm not showing you everything that can be done. I'm just showing you some of the basic things you can do. The rest you can discover in your own mathematical journeys. Here you have a division of expressions having the same base. When you're doing that, then of course the exponents minus. You're looking at e, x, l, and 2 minus x, l, and 3. Remember laws of exponent. Here isolate the x, e, exponent x. Then you're looking at l and 2 minus l and 3. So what was something which you couldn't do much with, now you have developed an expression which demonstrates that you could have done something with it if you only would think about this conversion perspective. Now let's bring some calculus into play over here. We've shown you the multiplication, the product, we've shown you the quotient. Now let's do something more. You're looking at something which looks like d or dx, a derivative, and of course you can do it any other way. I'm just showing you this being done with regards to this unique or useful conversion perspective. You know now b to the x is same thing as you looking at d or dx. Otherwise you'd be doing the product rule over here. You have two different functions f and g, you do the product rule, which is by no means hard. I'm showing you just another way. B to the x, you know, would be e to the x, l, and b, and then you're multiplying that with e to the x. Then bring everything here under a single unifying term, which would be e, x, l, and b plus x. That's exactly what you would have. And you can even isolate an x, but now you see what would have originally required a product rule can now be handled using the chain rule. If u is equal to x, l, and b plus x, then function with regards to u is equal to e to the u, and you can just use the chain rule, d or du, e to the u, and then du or dx. You have everything here, x, l, and b plus x. The derivative of these are easy. E to the u will stay as e to the u, and I'll leave that u blank. This x, l, and b plus x will come out as just l and b plus 1, because the derivative of this will just be the natural log b. The derivative of this will be 1. And you're multiplying all of this with l and b plus 1, which can come here as a coefficient. Then here you resubstitute the u, which is e to the x, l, and b plus x. And that right there is your answer. This could have been brought out here as a coefficient, and you know you've done this in a different way. If you did this using the product rule, I guarantee you it would be exactly the same. Anyhow, this right over here, you can rewrite it back, because you know this right here was equal to b to the x, e to the x, right? You can rewrite all of this, and I'm going to rewrite it for you right over here. You can rewrite that entire answer as l and b plus 1. That's my coefficient, and then e to the x, b to the x. That right there is the derivative of this, which you're seeing right over here. Remember, this entire expression here is this. There's no difference between this and that, alright? So you can see the derivative has been done using the chain rule for what was originally something intended for a product rule. Let me show you something more. We're looking at something which looks like this. Integral of e to the x b to the x dx. You could probably do this easily using a integrating by parts technique, but if you didn't want to do it, having to utilize two different functions, you don't want to do it, bring in this form right over here. We know b to the x is equal to e to the x ln b. You can substitute that right here. That's something which I verified for you. You're looking at e to the x times e to the x ln b dx. You're really looking at basically e to the power of x plus x ln b. That's what you're looking at dx. Now do the polynomial substitution. See, you don't want to do this using the integrating by parts. You want to do this using a polynomial substitution. If u is equal to x plus x l n b, then du is equal to the derivative of this, which will be 1 plus l n b dx. And then dx will be du over 1 plus l n b. And you bring everything here into play. You're looking at e to the u, and then you're looking at du over 1 plus ln b. This 1 divided by 1 plus ln b can come right here as a coefficient to your entire integral, and I want to do that. 1 over 1 plus ln b. And then I can eliminate this denominator here, and we can clean it up like this. Your antiderivative of e to the u is just e to the u. You can resubstitute that u, but you'll have 1 plus ln b here, and then you'll have this plus c, and then we resubstitute the u over here, and this u over here is x plus x ln b. But we know this e to the x plus x ln b can be resubstituted exactly for this, and we might as well do it. So in essence, all of this right here can then be converted into e to the x, b to the x plus c, all divided by 1 plus ln b. And this form right here and this form right here are equivalent, and that right there is the antiderivative of that. Remember, this useful conversion perspective is just optional perspective or conversion you need to be aware of. Maybe it has some real life practical benefits to you that you want to utilize, but you can always do questions without even having to do this perspective. And there are some instances where it's very beneficial to do it this way because it saves on time and it saves on work. But always remember, a power function can easily be converted into an exponential function because at the end they are indeed exponential functions, as very well this graph shows right over here. These are all exponential functions. Remember, e right here is just 2.71828 to the power of x. No different than these, except you have a different numerical base. Keep this conversion perspective right here in mind, and it could very well benefit you down the road. Thank you for watching. Stay tuned. Have a nice day.